Hey guys, so this video is a little different. I just wanted to take a look at the classic orbital elements and how they impact sort of the view that you see in the Rick space. We talk about the COEs quite a bit, and I think we have kind of an intuitive astrolab kind of understanding of what they do, but maybe not as intuitive understanding of how that impacts the Rick frame. So what I've done here is I've set up two 3D graphics windows, and I've got two satellites that are essentially the exact same satellite right now. They're both at GEO. They're approximately co-located, and Kepler satellite is a satellite that I'm going to manipulate according to the classic orbital elements, which you can see listed out here. So we have our semi-major axis, our eccentricity, our inclination, our argument of perigee, the right ascension of the ascending node, and the true anomaly. So in the 3D graphics window, you're going to see the Earth inertial frame, and then in this 3D graphics window over here, you're going to see the Rick frame as it pertains to reference satellite. So the first one, really easy to understand, the semi-major axis is just the average distance from the Earth, or really the center foci of the ellipse that an object is orbiting around. So you can see we can just slide this up and down, and it's producing two circles. Now, if this semi-major axis is not significantly different from the reference satellite, what it will appear is what we typically refer to as linear drift. You can see it's approximately a straight line. When you get really into the Rick frame, the curvature of the orbit starts to fade, and what you see is something that's akin to a straight line. Now, in terms of how this impacts your relative motion, the closer you are to the Earth, the faster you orbit around the Earth in terms of your orbital velocity. It's just that impact between your orbital period and your orbital altitude. So as you can see, as Kepler satellite goes very close to the Earth, you'll see that Kepler satellite is moving around the Earth more times in a single reference satellite revolution. And then as Kepler satellite's orbit grows beyond reference satellite, now it's moving slower. And when these semi-major axes are relatively close to each other, what we see here is something that looks like drift, where if Kepler satellite is closer to the Earth, it looks like it's drifting to the east, at least as depicted here. Just adjust those so that they're starting in the same relative location. So here you can see it, as Kepler satellite is closer to the Earth, it is drifting faster, orbital velocity around the Earth, shorter period than reference satellite, and it appears to drift to the east. Now if Kepler satellite is moved to be higher than reference satellite's orbit, you can see that now it's appearing to drift to the west, just due to the orbital motion. So fundamentally, the semi-major axis is going to be average distance from the center foci. We can put on some additional vectors so that we can see that. So this will especially become apparent as we see eccentricity, but right now, as you zoom in, you can see that the distance of periapsis and the distance of apoapsis are the same. What makes them the same is this second element that we're going to describe as the eccentricity, which is how elliptical is your orbital shape. So as you can see, the total length of these vectors, which is dictated by the semi-major axis here, has not changed. But what has changed is the distance from perigee and the distance from apogee. So what we'll do is set Kepler satellite's altitude to the geosynchronous altitude. And there it is. So now as we increase eccentricity, what we create is this shape that we call the natural motion circumnavigation. So it looks a little bit like this, just an ellipse that appears to orbit around the reference satellite. It's not actually orbiting around reference satellite, it's only orbiting around the Earth. But because of this elliptical shape and kind of following that same principle that we established before, when one of these objects is closer to the Earth, it's moving faster. And when it's further away from the Earth, it's moving slower. So there's periods when Kepler's satellite is racing ahead of reference satellite. If we zoom out, we can see that there's this sort of like almost orbital shape that appears around a reference satellite. And the more eccentricity you add, the more pronounced the shape gets. So just a larger and larger NMC. And what's really interesting is the more eccentricity you add, the more the impact of the curvature of orbits starts to come into play. And instead of getting this nice oval shape, you start to get something that looks kind of like the Chicago bean. This really sort of interestingly curved shape as the curvature of your orbit starts to become an impacting factor. And this is all due to this principle that you can see over here on this side. This is a highly eccentric orbit where we have a very low perigee or periapsis and a very high apoapsis. So that's the impact of semi-major axis. And you can combine these in any way that you want. So let's lower this eccentricity slightly. We'll go back to our starting status, and now we'll raise our semi-major axis. This is what we would typically refer to as a drifting NMC. So you still are seeing that elliptical motion, but we're also seeing some east-west drift here. And the higher we raise our altitude, the faster the drift. Until eventually you start to get shapes that look like this. All of these shapes that we've created still have the same eccentricity, but because of the fact that we are now drifting, because we're further away from the Earth than reference satellite in terms of our average distance, we're spending more time above its orbit than below its orbit, as you can see here. And so it appears that we are drifting to the west, what we would typically refer to as a drifting NMC. Okay, so that is semi-major axis and eccentricity. What about inclination and right ascension and ascending node? What do those do? Well, to see those, let's just return to our original starting location, and let's go ahead and add some inclination. Wow, look at that. So now instead of that in-plane motion that we were seeing from before, we're now seeing out-of-plane motion or cross-track motion. And if we go back to our 3D graphics window, the impact of the inclination is leading to a tilt in the orbit, which you can kind of see here. So the more tilt we add, the more pronounced the effect appears. You can see 1 degree of inclination creates sort of this almost straight up and down motion, and very hard to discern a difference. Whereas, 65 degrees of inclination, very easy to see a difference between these two altitudes. And it creates this, what we would call like a figure 8 or a hourglass shape. So what is inclination referring to? It is basically Kepler satellites tilt with respect to the equatorial plane. And we can kind of see that here. If we imagine sort of a plane that goes through the equator of Earth, then your inclination is how much is your orbital plane tilted with respect to that equatorial plane. So as this grows, you can see that angle of the plane changes. And what that does in a RIC frame is produce sort of this up and down out of plane motion. Now if we combine this with some semi-major axis change, we start to produce what we start to produce kind of these unique drifting, almost like a snake track. Looks kind of like this. So now we're seeing drift due to the fact that our semi-major axis is different, and we're seeing out-of-plane motion. But this drift rate is the exact same as if we had zero inclination. If we were to take this away, it doesn't change how fast we're drifting around the Earth, because your out-of-plane motion doesn't fundamentally change your in-plane motion. And we can do kind of the same thing where we set our semi-major axis equal to the target object, but this time we change our eccentricity, and we're still getting the exact same shape that we would get if we had no inclination in terms of in-plane. So here's that oval with no inclination, and here's that oval with 1 degree of inclination. You can still find the same oval, but now it's just been tilted or twisted around the reference object. It still has the same period. Okay, so that's inclination. What about right ascension of the ascending node? So right ascension of the ascending node describes the particular case of where, with respect to a standard reference, does your orbit cross the equator or ascend through the equator, so move from a negative cross-track to a positive cross-track, this point right here. So what we can see with these tilted orbits is we can change that point by changing our ascension, right ascension of the ascending node. So you can see it's kind of like a hula hoop that's about to fall. We're just twisting the orbit around. And the more pronounced we make our inclination, the easier it is to see kind of how this twist works. So now we have very high inclination, and we can sort of cause this disk to spin as we change our right ascension and ascending node. So we're changing the point with respect to a standard reference where our satellite ascends through the equator. So that is the right ascension of the ascending node. Okay, and now the last Keplerian elements that we need to look at in our RIC frame are going to be the argument of perigee and the true anomaly. Now, argument of perigee requires your satellite to have a perigee. Otherwise, what you'll see is that changing it is almost the exact same thing as changing your true anomaly. So let's just modify argument of perigee. You can see it just spins our satellite around in its orbit, which, if you were to manipulate the true anomaly, looks like almost the exact same effect. So how are these two different? True anomaly versus argument of perigee. Well, the reason they look exactly the same right now is because we don't have a discernible difference between our perigee and apogee. That's because our eccentricity is currently set to 0, so every point in our orbit is perigee and every point in our orbit is apogee. In order for argument of perigee to make sense and be visually distinct, let's add our eccentricity. So let's get a nice eccentric orbit like this one that's here. And now you'll see that when I change my argument of perigee, it is not the same as changing my true anomaly. So here's the impact of true anomaly. If you look in the right screen, you can see that what's happening is KeplerSat is changing to a different location in the orbit that is being depicted there. Now let's change the argument of perigee and see how that changes this screen here. So take a close look at this screen and watch what happens to the ellipse as I move my argument of perigee. So it's changing with respect to a standard reference where the closest point on the Earth, or the point of closest approach to the Earth. So with respect to the standard reference, where is your closest point to the Earth? So right now it's here over the Pacific Ocean. But if I want it to be over Africa, all I have to do is change my argument of perigee. Yep, so there it is over Africa. And you can see in RIC frame, these can become very important to look at. So let's say, for instance, I wanted to be in this NMC around reference satellite, but I wanted to be at this point at this time of day, which is, let's say, midnight on the 15th of April. So instead of being here at midnight on the 15th of April, I want to be up here. The first thing I'm saying is at this time, I want to be at my apogee, which means I need to shift my argument of perigee by 180 degrees. So let's go ahead and do that. All right, so now that has happened. I've placed my apogee at the place that I want, but you also notice that my satellite is now on the other side of the Earth. So I also need to now change my location in true anomaly of where I am at this current time. So let's just move this back 180 degrees. And there you go. So I have changed the point of my apogee, and I have moved my orbit back to the point where it would be traveling with reference satellite. And this relationship kind of exists. So let's say that I wanted to be here, crossing the geobelt to the west of the target. So let's just go back to the starting status of 0. Okay, so what do I need to do? I need to shift my perigee by 90 degrees. And then I need to back up in true anomaly by also 90 degrees. So it's not exactly what I was looking for, because now my center of mass is causing me to oscillate around this object. So there's a couple different ways I can dial this in. And there we go. So I've manipulated my right ascension to ascending node, my argument of perigee, and my true anomaly so that I can put myself into an NMC that is about what I was looking for. And I can dial these in more specifically. So there you have it. That's just kind of a quick teach on the 6 classic elements or Keplerian elements or classical orbital elements and how they can kind of change your location in the RIC frame. And you can combine these in any manner of ways to create some really unique shapes. So hopefully this helps you better understand how these elements work and how they can change your RPOs for future problem solving.